But we have to move on to the last topic, feeding ecology. A blue whale's diet is very limited. A few amphipods here and there, maybe some small crab-like munida, but for the most part, almost entirely, blue whales subsist on a strict diet of krill, a small, shrimp-like crustacean of the genus Euphaucid. Remember that krill are one of the very few trophic middlemen between whales and geology. It is an insane enterprise, the largest animal in the world living strictly on one of the smallest. In a moment I will explain exactly what goes on during a blue whale's lunge feed. But before I do, I need to impress upon you just how expensive a blue whale meal is, energetically speaking. In fact, eating like a blue whale only becomes worthwhile when the whale is engulfing a patch of krill at least a certain density and at an ideal depth, and when the whale is at least a certain size. So there's a sweet spot. The deeper the krill patches are, the fewer lunges it can do per dive. The shallower and denser the prey patch, the better. Size is key to feeding efficiency in blue whales. In fact, it may be the primary reason they are so large. Size does matter, especially, strangely enough, the relative size of the throat. In fact, because of its proportions, a blue whale's feeding behavior is several times more efficient than that of other whales, even the other lunge feeders in the blue whale's family. Because blue whales and the patches they pursue are so huge, simple fish finders can give us glimpses into what is going on during a blue whale's feeding dive. On the left, you can see the whale as it charges up from below into a krill patch. Here is a dive profile of a whale doing a series of steady feeding dives. The oscillations at the bottom of each dive represent feeding lunges, averaging about 4 lunges per dive. She dove down below her prey patch and charged up into it, and repeated. Note that each lunge entailed a fierce upward sprint, losing 150 feet of depth in only a few seconds. This is a massive and rapid change in water pressure. Here's a close-up of one of these feeding dives, correlated to krill swarm imagery. The green dots signify when the actual lunge occurred. You can see from its dive profile how it charges up into the prey layer, lunging right as it enters. Here's another profile of several dives through an uneven and patchy zone of prey. You can see that the blue whale adjusts her dive depth and duration according to where the prey is. We still have no idea how they navigate during a feeding event, or how they locate the densest patches. But we were trying. We would get out in our trawler and first seek out a feeding event, an upwelling zone in which one or more whales were lunge feeding. We wanted answers to 2 questions. Number 1, what are the average densities of a swarm that can get a Corcovado blue whale's attention? And 2, how patchy are these swarms? As in, what are the maximum and minimum densities within it? We would then attempt to conduct a series of biased and unbiased plankton trawls. Unbiased trawls were just random samples taken within the general feeding area, while biased trawls were those conducted based on clues from the whales on where the krill patches were. This usually entailed trawling right alongside or right behind the lunging whales. This tended to be pretty intense. I was always assigned to managing the ropes and the net, which required constant attention and tugging. My coworkers would point, scream, and gasp as up to 6 whales would surface lunge all around our boat, and I could hear the huge waves and their mighty breaths right over my shoulder, but I was never able to stop and stare. It was the worst kind of torture. Many researchers have dedicated their lives to understanding just what it costs for a blue whale to lunge for food. They employ extensive computer modeling and even use elaborate simulations with giant parachutes to comprehend exactly what is going on. Using extremely sensitive tags, researchers can also monitor the depth, speed, rolling pitch, even individual fluke strokes in each moment of a blue whale's dive. Using this technology, we now have an idea of the energetics and kinematics of a lunge feed. This is how they do it. First, our whale has to find some affordable swarms of krill. As I said earlier, no one knows how blue whales locate their food. Utter mystery. Moving on. Then she dives down to the prey layer. As we've already seen, she dives below it, then turns back up into it. She then accelerates to high speed towards a particularly dense patch. The purple line here is speed. Again, no one has any idea how they locate the densest patches within a swarm. Utter mystery. Moving on. She attacks. It is a huge forward acceleration, and the whale begins to open her mouth. Once her mouth opens up to a threshold angle, which is still very small, drag immediately begins to slow down the whale. Within a couple seconds, her jaws are opened to a full 90 degrees. Spanning a quarter of her body length, her jaws are the largest bones in her body, the largest bones in the world. The drag caused by opening her mouth at high speed causes the effortless inflation of her throat pouch, known as the buccal cavity. Then, grotesquely, her tongue inverts, of all things, folding into itself, and makes available a huge volume of space. The buccal cavity grows larger still with the help of specialized throat blubber, known as ventral groove blubber, or VGB. The VGB spans half the whale's body length, can expand like an accordion, and makes the whale look like a nightmarish pollywog. Her lower jaws can even rotate outward, thanks to a third joint in the front to expand the circumference of her mouth trap. Will she stop at nothing for a bigger gulp? To summarize, the blue whale holds a lot in her mouth, up to 60 tons of water. That's the same volume as a school bus. So her massive maws open, and water rushes into its enormous vacuum, sucking krill and all other debris in with it. Nothing can escape. Imagine all the driftwood, trash, and jellyfish these animals accidentally swallow with every lunge. Like a parachute opening, the 60 tons of water she is pushing along in her mouth adds enormous hydrodynamic drag to the moving whale. This is called engulfment drag, and is compounded by the increased drag from water that flows around its balloon body, which is called shape drag. The combined drags dissipate the whale's kinetic energy, bringing her to a near halt. And then, just like the way you can close a van's sliding door by pulling forward then abruptly stopping, this rapid halt, induced by its own drag, makes it possible for the blue whale to close its mouth. But even with that help, this is one of the greatest biomechanical forces on Earth. After mouth closure, muscles that crisscross the VGB contract and depress the buccal cavity. At the same time, the tongue is uninverted. In what is known as the purging phase, these actions push the water through the racks of baleen dangling from its upper jaw and trapping the krill inside. With a huge sweeping motion of its 2-ton tongue, the krill are tossed back into the abyss of its esophagus, the blue whale's lunch feed. Of course, all of these branches of cetacean research add up to the highest priority, which is conservation. Despite all the whales we would see every single day, it's important to remember how incredibly endangered they still are. Keep in mind, the Antarctic blues are currently at only 1% of their 1905 population. What would it have been like in the Gulf of Corcovado 100 years ago? Even if we stay conservative and guess that the Chilean stock was reduced to 5%, rather than 1% of its original population, that means there would be 20 times as many whales in those fjords today. Here's an artist's rendering of what that would look like. Here's Corcovado in 2011, and here's Corcovado in 1911. 20 times more whales. Whale soup! There is an alarming amount about whales, particularly whales in fjords, that we may never understand. How do whales orient themselves in complex habitats like scary arrays? Why do blue whales sing? How do they sing? What are they singing about? Why do humpbacks breach? What are orcas saying to each other? How do blue whales locate their food? How do they find the densest parts of a krill swarm? What's the deal with offshore orca? Can I ever become an honorary member in a humpback feeding group? There is so much that is so hard to learn, but this is as exciting as it is daunting, for wherever there is mystery, you are bound to find discovery. Just like, wherever there are geologic marvels, you are bound to find whales, and vice versa. Cetologists are trying to study whales that are at the surface less than 10% of the time. When they are at the surface, only about 10% of their bodies are showing. That's 10% of 10%. 99% of their lives remain an inevitable mystery. In terms of our trusty blue whale scale, we only understand about 1/4 of their flukes. Geologists are also reconstructing natural history based on the few, patchy, discontinuous, surface-deep records they have access to. So, rocks, whales. Both branches of science are trying to bring coherence to subjects that lie, inevitably and by definition, outside of human understanding. In doing so, they remind us all that there must always be a place in the scientific process for imagination, for adventure, and, above all, for wonder. Thank you.